Welcome to this video on introducing two-sample hypothesis testing with dependent means, also called matched pairs. Let's begin. Objectives. After watching this video, you should be able to explain why hypothesis testing with dependent means is necessary, state the null and alternative hypotheses associated with this type of hypothesis test, and compare the procedure and hypothesis statements for hypothesis testing with dependent means with that of independent means. Why dependent means? As the name implies, two-sample hypothesis tests consist of two samples. Sometimes these two samples consist of before and after treatment data. For example, suppose a randomly selected group of 500 people across the country participated in a 6-week weight loss program. To properly analyze the data, you would need to compare each person's weight before they started the program with the same person's weight after they completed the 6-week program. Suppose two friends, Sally and Bob, participated in the program with the following results. Would it make sense to compare Sally's before weight of 150 pounds to Bob's after weight of 240 pounds? No, it only makes sense to compare each person's before weight to that same person's after weight. For this reason, hypothesis testing with dependent means is also sometimes called matched pairs. Comparing each person's before weight to that same person's after weight allows us to calculate the difference D in before and after weights. As you can see here, we've taken 150 pounds and subtracted 145. 150 minus 145 is 5. That indicates that Sally experienced a 5-pound weight loss during the treatment. Similarly, for Bob, his weight before the program was 250 pounds. His weight after the program was 240. 250 minus 240 is 10, so he experienced a weight loss of 5 pounds. So as you can see, as we do this, if we had 500 rows of data, we would have 500 differences. And so then what we do is we go through and calculate the mean difference, the mean sample difference, which we would call D bar. Remember, the bar indicates a sample mean. So if the weight loss program was not effective, that would mean that on average the group as a whole did not experience a statistically significant weight loss. Therefore, our null hypothesis would be that the population mean difference is equal to 0. This is equivalent to saying that the mean weight loss is 0, which implies that on average participants did not lose weight. Recall that to find the difference D, we had to subtract our sample values. As we did here, 150 minus 45 is 5. 250 minus 240 is 10. Before we can write our alternative hypothesis, we must define the difference D between the matched pairs as either before minus after, or x1 minus x2, or we would have to define it as after minus before, or x2 minus x1. Please note that it really doesn't matter which you choose as long as you are internally consistent throughout the problem. In the table above, we already chose to subtract to do before minus after, or x1 minus x2. So we already made this decision, and as you can see, these positive numbers indicate a weight loss. So if the treatment program was effective, that would mean that our average difference is larger than 0. So this is our alternative hypothesis. Mu sub D is greater than 0. However, it's really important to understand that the order x1 minus x2 or x2 minus x1 is arbitrary. We could just have easily have found the difference of after minus before. In other words, we could have asked or we could have calculated 145 minus 150 and found the difference to be negative 5. And that might be preferable. Some people might want this value to be negative to indicate a loss of weight instead of a gain of weight, right? And again, Bob's would be negative 10 instead of 10. If we define our difference D as after minus before, then a negative value indicates weight loss, so that would mean that the alternative hypothesis would have to be mu sub D is less than 0. So again, it's very important to understand and note that how you define or how you state your alternative hypothesis is determined by how you define your difference. Is it x1 minus x2 or x2 minus x1? And again, the decision is completely up to you. Just don't change it halfway through the problem. Make sure you're consistent throughout. All right, so let's sum up what we've learned so far. Before we can write any of our hypothesis statements, we have to define the difference d between each matched pair. So it's either going to be x1 minus x2 or x2 minus x1. Again, it doesn't matter which one you choose as long as you are consistent. Once you've made your decision, then you can proceed to write your hypothesis statements. So the null hypothesis, regardless of how you determine your difference or define your difference, is always going to be the same as mu sub d is equal to 0. And then your alternative hypothesis has to be one of the three following statements. Either your mean difference is negative, so mu sub d is less than 0, or the mean difference is positive, mu sub d is greater than 0, or you're not sure which way it's going to go, so you have to consider both possibilities. So you would simply say that mu sub d is not equal to 0. To enhance our understanding of what we just learned, a good exercise is to compare the process of starting a hypothesis test with dependent means to the process of independent means. So the first question I have is how many means? So we have two samples, right? But from those two samples, we generate a single mean, which is the mean difference in the two populations. Let's compare that to independent means, where we actually have two independent means. We have the mean of population 1 and the mean of population 2. So our general procedure for dependent means is to, again, find a single mean, which is the average difference between the matched pairs. Conversely, with independent means, we compare two sample means to each other. With dependent means, we actually subtract first and then average second. So in other words, we take each row of data, right, and we subtract the first column minus the second column, or the second column minus the first column. Again, our decision is arbitrary as long as we're consistent. And so doing that, we have a column of differences. And the number of these we have is the same as the number of data points we have. And so then what we do is we take all of these differences and we average them together. And we find that average difference, which we call d bar. Okay. Conversely, if we're working with independent means, we calculate the means separately. So we have a sample mean for the first column of data and a sample mean for the second column of data, and then we don't subtract them until we go to calculate our sample statistic. Okay, and then when we look at our null hypotheses, the null hypothesis for dependent means is this mean difference is equal to 0, meaning that there was no difference, there was no change in the two columns of data. Okay. Conversely, with the independent means, we see two different means represented in our null hypothesis. We have mu1 minus mu2 is equal to 0. Okay, and then last but not least, if we look at our alternative hypotheses for dependent means, again, we can just see this single mean represented here, the mean difference. And again, in the independent means, we have two means represented here. So now that you've watched this video, you should be able to explain why hypothesis testing with dependent means is necessary, state the null and alternative hypotheses associated with this hypothesis test, and also compare this procedure and the hypothesis statements associated with hypothesis testing for dependent means with those of independent means.